So it's getting recorded, right?
Yes.
The first question is like, so prime number of set bits in binary representation. We are given two integers, they are left and right LNR, and we need to count the number of numbers in their range this. Both are inclusive and having a primary number of set bits in their binary representation. So yeah, it's like example they have given, recall that number of set bits an integer has the number of ones present when written in binary. So what happened? Hmm. So from 6 to 10, if you see, 6 has two set bits and both, and 2 is a prime, so you can include it. 7, 3 and 3 is prime. Again for 9 same. For 10 also it's same. So total number is 4, and same goes for this. You'll have 5 here, and your LNR will be integers in the range of 1 is 1 at max 10k, at most 10k. Yeah. Hmm. So any queries, like how do you approach in this?
So, sorry, I'm first time joining. Is it like you can just say what you think might be a good approach? Is that
Yeah,
okay too?
sure.
Okay.
Sure.
Okay. So I have not seen the problem, but just by looking at it, we can
Okay.
definitely find the number of ones, right? Uh, if we write, if we keep right shifting and doing an end with one, then the rightmost bit, if it is one, then we will detect that it is one. Uh, so we can keep a count of the number of ones, and then we keep right shifting the number till we reach 0. So that should give us the count of ones, and then we have to detect whether that count is prime or not. So either we have a function for that, but it looks like by looking at the range, maybe we statically just say that, okay, if the number is going to be, what was the maximum they are saying?
10k per 6.
So that means it's like 10, 100,000, 100 is a 100,000?
10,000.
No,
Thou-
thousand. It is 10,000.
1,000.
No,
So
it just.
Oh,
Yeah.
okay.
Go
Yeah.
ahead.
One.
Yeah. Go ahead.
so that basically is 1,000. So 6 zeros. So you need 10, 100,000, 10,000, 100,000 million. So I think 2 raised to 20 is a million, if I remember. So that means our maximum number of twos can be, maximum number of ones can be 20. So we just can statically say like the primes between 1 and 20. So I don't know if two I think we consider prime, right?
Yeah.
Two, then
Yeah.
3, 2, 3, 5, 7, then 11,
11.
13, 17, and 19. So if that is then we return true.
Yeah.
Yeah.
That's good.
Perfect.
Yeah.
Mhm.
I mean, I followed the same approach.
Yeah,
Just
word, Sandeep.
identify like number of ones in a number and check if it is a prime.
Yeah. You want to share code like?
Yeah, sure.
Sure.
Let me know when you see it. When you see the screen.
Yeah, it's visible. Can you increase the font size, please?
Sure.
A bit. Yeah, that's it.
I know.
Is it too big?
That's fine.
Okay.
Okay.
So we have a lower and right bounds. So I'm just looping through the lower to upper bound. So this is like inclusive. So I'm using equals. So I have two methods. So one is a bit counter, so which will count the number of ones in a number. So so I found this way, like, when you do a AND operation on n into n minus 1, you can get the number of you can count number of ones in a number.
Set bits.
Yeah, a number of set bits in a number. So once I get that, I'm just checking, if it is a prime. So for a prime, I have like one more function. Yeah, I mean, I actually, when I wrote this, I didn't, think about, like, that we just talked about, like, the number of primes, like, it will be definitely less than 20. So
Yeah, Jagrut
that's
mentioned that.
that's an optimization, but I'm always checking whether it's a prime. Any questions?
So the bit counting you are doing on 19, line number 19, right?
Yeah, 19. Yeah. So I found one article like long time ago when I was reading about it. They said, like, counting number of ones, this is a like most optimized. This takes like, max of log n in a worst case,
Okay.
because this takes only number of bits, right? Because every time you would do a AND, so let's say if the number of set bits are 3, this loop runs only thrice.
Right. Yeah, I think someone mentioned that last week or so. Yeah, okay.
Okay.
Good, yeah.
Yeah.
So how much time will it take? Like,
You are asking about the time complexity in that?
yeah. So
Oh, time complexity.
reshare it if you can just.
Yeah, sure. Yeah. So this we are running it for O of n, right?
Yeah.
And this one, checking the prime number, this would be like, square root of n. So that is like n into square root of n.
It's log n, right? That's
And
Yeah.
log n.
Yeah, log n is
Is it log n or?
no log n into square root of n. Because for every number we not every, every number we check if it is a prime. The prime method is not O of 1, but it's a square root of n.
Okay.
So to check prime number, we have to just go till square root.
Yeah. Because
The meat of the number, to meat of the number you have to go. Yeah, that is square root. It's fine.
Yeah.
Meat of number is square root or divided by number?
When you divide by number, what happens is, like, let's say if you take 36 number, right? So the factors of 36 are like, if you start like take A and B, it can be 2 and 18, right? So at a point you reach like, 6 and 6, like 6 into 6 is 36. If you take like numbers greater than 6 and 6, it is always like, it repeats the same numbers, like 2 and 18 will come as like, 18 and 2, right? You get you see a repeated factors after the square root of n.
Okay. I think, yeah, that's a good point. I think, like Shashank was mentioning, might be people think like go till half, like mid, but mid is not needed if we are going till square root.
Yeah, right. I'm stopping this share.
The logic behind mid was like number in itself, and if you get any factor between the mid, that means that's not a prime, right?
No, here square root is not, I think, exactly mid.
Yeah, this is not exactly like, but what he was saying, like repeated factors will have.
So is it like a constant time for actually calculating the prime as well as the bits? Right, because if we use the way Jagrut said, we can make
Hmm.
that constant for
Yeah.
finding the primes, right?
Yes. Yeah. We can make it
Yeah.
constant.
And the finding the bits also will be almost constant, right? Because it is 32-bit max.
Yes.
Then L minus R is also 10K only.
Yeah, but that is
Just
actually the range, right? We always have a variation in that. So that can be O of
mm,
n.
yeah, yeah.
I'm just thinking loud. I'm not sure. So I just.
So makes sense. I think it should be like not sure. So here I think the same optimization what Jagrut was speaking, right? Says
Mhm.
speaker. So this is like from 2 to 20, all the prime numbers, and I'm using this exactly what do you say library itself to convert it to the binary.
Mhm.
Or actually is like this is if we have any number to get the set bits. Let's say if we have three, what do you say? If three only we have, so three is what 8 4 2 1 if we put. So this is our three, right?
Mhm.
So just we do and if we found that this is our one after doing and of these two, then we'll count bit as one. Next again I'll do right shift. Now this one will come over here and 0 0 and 0. So
Mhm.
again it will have one. So we'll have two, and after that all are zeros only. So total number of bits are two. So actually that is the way I should have done, but here I'm directly using the what do you say library of in the Python. I mean in other languages also it might be. I'm not sure. And this is just counting how many ones are present in that binary representation.
Okay.
You know, and that's returning the result.
So but the time complexity will be like O of n log n, right? So even in
Should be
this,
because binary.
yeah, because we are actually getting the counts of the bits, right?
Yeah.
So it is square root. So it should be at least log n, no?
That finding binary, no.
Hmm.
Yeah, it should be log n
Okay.
because we are dividing every number by two and getting the bits out of it, right? I mean,
Yeah.
we are doing the right shift. Right shift means what? Dividing every number by two. So log factor will come because of it, because of that. So log n base 2 will be for binary, and this one is like order of n for loop. So n log n or something n log k by 2. So but log factor will be there.
Mhm. And
Mm.
also you saw in the chat, Roger mentioned that we did something recently uh,
Mm.
that can also be used to implement this problem. Was he talking about the digit DP? But he said that might be an overkill.
Yeah, that just below this, what is the problem? He has mentioned something.
Yeah. So was he talking
I
about the
think
digit DP?
I exactly don't remember.
Okay.
Something was telling some easy method, something. I mean, I'm getting a not a clear picture of it.
No, no,
So
he
it
said
was,
that. Sorry, go ahead.
yeah, no, so go.
So he was talking about this easy problem. This was the easy
Hmm.
problem, right, for today. And then he said that we did something recently, and that also can be applied for this problem, but it might be an overkill.
Yeah, definitely digit DP.
Yeah, then it might be DGDP. Yeah, okay.
Hmm. I think that is for finding the prime numbers between two range. You can use digit DP for finding the prime numbers between two numbers like a range. But it is like you are converting it to binary first, and then checking bits present in the binary representation is prime or not. The more modification, yeah, it can be done using digit DP, but that is be too much, I think, for this one, right?
Yeah.
Mm. Yep, then you can switch to next. Or any code, something wants to some share something, somebody.
No, I think this is the only
Oh,
thing what
everybody, yeah,
comes
most
to,
of
right?
them.
Yeah, it is almost the same. Yeah. most efficient
So this is
one.
like, yeah. Mhm. It's like checking the completeness of a B tree, and sorry, binary tree. Binary tree is given. We need to find whether it's complete or not. And the complete binary tree, every level except the last one is completely filled, and all the nodes in the last level are as far as possible. And it can have between 1 to 2 keep RH nodes, including the last level at H. So this is your complete binary tree. Last level you can miss, like here they are, what is it, missing. So it's true, and this is false because you are
Yeah, you don't have
first
a
left,
left. Yeah,
first left and then right should have been
yeah,
right.
yeah.
Mm. It's a heap like property, right? Heap also starts from left to right only. We can't have nodes like here. It should first fill the all the left and then go to right.
Heap is a complete binary tree, correct?
Oh, heap is a complete binary tree. Yeah.
Yeah, I think we can use the heap here, like heap like property.
Property. Yeah.
Mm.
So
And
heap,
yes, go ahead.
I was telling like a heap generally stores value like in an array. So if you
Uh,
see, and if we know how many elements are there, and then start doing like how we do in heap, we can find out if the number of elements are, it is within the range of number of elements or not.
Mm-hmm.
Could you please
So,
repeat? Sorry, I couldn't follow you.
so in heap, there is a property pair for any parent, the children would be, if parent index is I, the children would be 2i or 2i plus 1.
Correct.
So, so that means if something, so in the first example, how many nodes are there? 1, 2, 3, 4, 5, 6. So, so the so the index range should be between 6. If I'm at node 3, its children are so node index, like say node 3 index is 3, 1, 2,
two,
like
Two.
2, and 2 into I is
4 plus 1, 5.
4, and 4 and 5. No, actually,
two.
if you're starting with 0, then I think we have to do plus 1 and plus 2.
Right, right.
So it would be 2i plus 1 and 2i plus 2. So it would be
Hmm.
5 and 6.
Yeah.
Mm-hmm.
6 is empty.
And 6 is empty, and there is nothing. So total elements is also 6, and so but if you go by indexes, total index range is 0 to 5. And 3 told I have 5 and 6, and there is no 6 index, so that is good. But if you go to example 2,
So
so 3 will say I have I supposed to have two indexes. One is this 5 and another is 6. But the total
hmm.
elements should be from index 0 to index 5. So something is outside that. So that means this is not correct.
But heap creation will have to do, or
No,
we
no,
have
no. We won't do heap creation. We'll just use that property of finding my children. What would the index of my children? And see if that would be a heap, whether the array could contain the children or not. So if it is a heap, or when I say heap, if it's a complete tree, the array index would contain that children. Otherwise, it should be outside that.
So you mean to say you are trying to copy the whole tree into an array?
No, 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 no. What I'm trying to say, let me do a whiteboard.
actually Asim, the tree node they have already given. It is a tree node pointer. It is not based on. It is not an array based implementation.
Agree.
So
So, like,
normally you can use a BFS, right? You can use a BFS and
Yeah.
store a
no,
No,
tuple in the queue.
So we can do a BFS. That is also a good idea. But I was trying to say if so first 0 to 6.
I think it is more work actually, because you'll have to traverse the tree to count how many nodes are there. Or
Yes. No, but I'm telling this is one approach. There is always another approach to approach.
Yeah.
So,
So in
I
this,
followed the same, but using a BFS.
Yes, I know there is a
Definitely
BFS.
will come to that. Yeah, let us see what he has to say. Yeah.
I'm
so
telling. Okay, if you guys want to jump on BFS, I'm
no,
fine
no,
with.
at least I would like to just know, once you create that array, then how
No
are you
array.
navigating?
So
Sorry, sorry, no, my bad. No, you just, this structure already given to us.
Mhm.
You basically are navigating the tree and filling it up.
No. So I'm
Okay.
just counting the nodes. So first function will count the nodes, which is 7 nodes, and it will tell if it is a complete tree. The range would be 0 to 6. If that would have to put in an array.
Yes.
So now again I will do struct reversal. So here my I will be 0.
Mm-hmm.
Its children are so here it would be 2i plus 1 and 2. So still these guys are within the range 0 to 6. Then
Yeah.
here it would be uh, 0 1
Three.
2
3 and
3 and
4.
4, so that is also in the range, and here it is 5 and 6, that is also in the range.
So,
Yeah,
Asim,
yeah.
by saying 3, 4, 5, 6, the level order traversal, you must be using BFS already, right?
No, I'm not doing level order traversal. I'm doing a recursion here. I'm just telling. So let's do any kind of traversal, like a pre-order.
But
So
what I'm saying is,
hmm,
2 was coming with number 1, but we wanted to assign 4 the number 3. How are you doing that?
assign 4 number 3. So yeah, this. So what I'm doing when parent will. So let's say there is a helper function. So when parent will call like say node dot left, it will pass like how we pass the levels. It will pass 2i plus 1, and same for the right side. It will plus 2, and it
Okay,
and the first time when the helper is called, it will send root
okay. Got it.
and 0.
Got it.
So, so for now, I'm not doing level order traversal. I'm just doing simple recursion where parent will call its children, and in the base condition, I will say, okay, now I got some index 2i plus 1, whether it is in the range or not.
Okay.
So if 7 is missing, 5 is still in the range, right?
7, yeah. So in this example, this is a complete tree.
Yeah, this is, let's say 7 is missing.
So let's say 7 is missing. So now my range
Okay.
would be this 0 to 5. As soon as this guy will come, it will be outside the range. And I
Okay.
can say this is not a complete tree.
Yeah. Makes sense.
Mm.
so
But
at
in,
node 3, when you are at node 3, you are checking that plus 1. So let's say, so if node 1 were 0 index,
Mm-hmm.
node 2 is index 1, and
Mm-hmm.
node 3 is index 2. Huh? So
Mm-hmm.
3's left child will be 2i or 2i plus 1, however you
2i plus
implement
1
it.
and 2i plus 2.
Okay, so that means 2i plus 1 is 5.
Mm-hmm.
So when I go to index 5, I will
No,
have some.
there is no left, so I won't go even that side.
Okay, so what check we do at 3 again?
No, so 3 is fine. 3 is at index 2. That is good. When 3 will call this guy right side, when it will call and dot right and send like 2i plus 2, that time when here some base condition would be there. So if whatever index I'm getting, whether that is in the range or not.
Yeah.
So that time I'll say, oh, it's not in the range, return false. You don't need to even go inside that.
Okay.
Is that clear or still there are?
Can we try one another input?
Yeah.
Let us try. So 1, 2, 3.
Mm-hmm.
Then 2 has only right child. 2 has only right child.
Okay.
And say it is 4. Yeah.
Nice. Okay. How many nodes are here now? 4.
Mm-hmm. 0 to 3.
Range would be 0 to 3 if it is a complete tree.
Mm-hmm.
Now what will happen? Here it is 0. Here it is 1. Here is 2. If there is a children here, it would be 4. And it would be 0, 1, 2. No, it would be 3.
4, yeah.
And it would be 4.
Mm-hmm.
So this side we won't go because there is null. As soon as I'll go,
yeah,
that is
it's working.
And I can say, okay, bye bye.
Yes.
So if 3 is there, then it's a complete binary tree, right?
Yeah, no, if, or let's say this 4 was this side, then yes, I can say this is a complete tree because we are filling from left to right.
Yeah, no, I'm saying 2's child is 4 and 3. Then
2's child
4 and
is,
5. Let's say 4 and 5. 2's child is 4
yeah,
and right
then
child is.
how many
It's
number
a
are
complete
nodes?
one.
5. Range would be 0
5.
to 4. And that time I'll say, okay, everything is in the range.
No, okay.
Yeah, makes sense. Yeah.
So you keep 2 variables here, one for the range and one for the...
Not range. I took range to explain it. You only need the number of nodes using this -1 because there's no range like this. We don't need to check if it's between 0 to 6. It should be only less than equal to 6. So the check is not a range check because we are incrementing from 0, 1, 2, 3, 4. So the only check is, or probably I think if I can show the code, that would be much more clear.
What is the order of traversal? Are we doing the pre-order?
Yes, counting nodes could be pre-order and doing this is also pre-order.
Both pre-order.
Okay. Very nice.
Yeah, it's
So
very
I know
interesting.
there's a BFS solution that is also interesting, but I thought, because when I saw this thing, the first thing came to mind, can I use something around heap?
Yeah.
Then let me share how to stop. Let me know when you can see my screen.
Yeah, it's there.
There is a zoom button. For some reason I can't see my zoom.
On cursor itself, you roll the fingers.
Yeah, my cursor is not working that well today.
When you're on Zoom window, it is not working. Yeah,
Okay, control plus.
Yeah, control plus.
Okay, so what I did, this is simple thing to count the nodes. Nothing fancy here. You can use any function to count the nodes. And then over here,
Okay.
The second time also is traversing the tree. Then only is checking the index at there. No?
yeah, there's no other way to do that. And I am not doing a +1 or +2 because I've signed only 1. If I have signed 0 from here, then I would have to do like this.
Yeah, that.
No, minus.
And then I'm doing like if this index would be, because this is total, then I have to do -1 then. Little variation.
Yeah.
Or, oh, that was greater than only. Equal to will automatically be covered.
Yeah, so if it is 0 based, then it is I+1 and I+2. Those are the children, right?
Yeah. To make my calculation simple, I just saying like, up to us. how we want to do.
Or even if it is 1, there also you can do +1 +2, no problem.
Let's see the calculation.
Because if your root is 1, the child will be 1 into 2 plus 1, 3, and it's just a reference, a relative point, so
Yeah,
doesn't
it's
make
just a kind of reference, right, to maintain between child. Yeah. No, but our
left and right.
calculations can go for a toss. So you see this guy. To bring that in the range. The reference could be, you're right. I can even put something +3 +4, but this is to get this within the range, that is the catch.
Yeah, that's a heap property we are using there, right? Yeah.
Mm-hmm.
Yeah, I see, but yeah, this is a very interesting way to implement.
Mm-hmm.
But the standard way, what everyone thinks about first is like the BFS or other way. So because it involves a single traversal, you are using twice.
Mm-hmm.
So is there going to have an impact on the time? Slight impact?
Yeah, time-wise, they go to order of n.
Yeah, I don't think it is impacting time because we are only doing 2n, 2 times traversal, right?
So, but 2 pass is doing. In BFS, you'll have 1 pass.
So
That is
the
also
way
different.
the way I think there's a plus and minus by looking at this. So here here it's very nice that we don't need any extra queue space. But so if we have a very big tree and the most of the nodes are going to be in the leaf level. So if it's a big tree, then our queue size will become big, which in this case is not happening. And in this, it looks
Index,
like, huh?
index will become large now if you have large number of trees. So again,
Huh,
index. Do you think index will be
index,
very large number?
correct.
We'll still use the extra stack space, right? Because if it is too deep, then the stack will be more.
Yes, in this, if it is too deep, then it will go. The stack space will be there, and it looks like you will early exit from here. So because if the problem is on the left side of the tree, you will probably detect it earlier.
Yeah.
That what looked like to me. Correct me if I'm wrong.
Yeah, you're right. If the tree, it's easy to identify here, like, okay, like,
But on the space,
What I'm asking is like, I think in the solution when you ran it, how much did you get time for this implementation and the BFS? Do you have a comparison a bit?
yeah, I have a comparison.
Okay.
I think I did a while back.
Okay, no problem.
So let's say which one is
It's
BFS.
almost 0. Okay, that is great.
The 0 every time, everywhere I've seen. I don't know why, although it's running, but still.
Okay, so this is so
Doesn't have much of
this
it.
is 0 milliseconds. The BFS is 1 millisecond.
Okay.
Yeah, so this is
That
you guys are
that
telling the BFS way.
I don't believe these numbers. If they're so small.
yeah.
But they are equal, right? It means it's nothing big of a deal.
So on what basis do those numbers are generated? Like that code is taking 1 ms time to execute.
No, I think they do a profiling for each function, and they get the average for each and every test case.
I think, yeah. Let's see. Might. Okay. Anybody wants to talk about BFS solution, or you want me to talk?
Let me talk.
Okay. Cool. I will
Yeah.
answer.
I don't have anything, so you can still keep showing your screen. But what I was thinking is in BFS, what we can do is while adding the nodes, if any time we saw it doesn't have a child, then we'll just set up a flag. Now going forward, there should be no children. If that is false, then somebody lower in the label or to my right has a child, whereas I don't have a child. That is not allowed in complete binary tree.
Complete tree.
So once that flag is set, if there is a child anywhere going forward, that is false and just exit from there. Otherwise it is true.
Yeah, I think he did the same way. On line 19, he's checking that and then returning false. Right, Asim?
I
You
think
are, yeah, he's using the same flag.
Rajendra, could you repeat that?
Saying is what I sorry. Yeah, you guys can hear me, right? Yeah.
Yeah.
So what I was saying is looking at the complete binary tree property. If I don't have a so at any level, once I how should I say it? Basically, once I see that I don't have a child, nobody to my right should have any children, and the next level also there should not be any children. I mean, for the nodes in the next level also there should not be any children. If you can pull up the example one, then probably it will be better. Yeah, in this case, what I'm saying is 3 doesn't have a right child. Once I saw once I saw a node which doesn't have a child, left or right doesn't matter. I'll obviously start from scanning from left only. But if I saw I was expecting a child, it is not there, I'll set up the flag. Now, suppose 3 doesn't have the left one as 6, it has right one as 6. But I know the left one is not present. That means 3 should not have a right child anymore. So once I was expecting a child and it is not met, that means going forward, anybody in the queue should not have any children whatsoever. If it is there, then it is not a complete binary tree anymore.
Yeah, correct. So people got that point, or more discussion around that?
It would be good to just quickly run one example.
Paul is for popping out.
See,
Yeah.
see what is happening right now. We'll keep on adding nulls also in this queue, like what solution I did here. So keep on adding nulls also, and if you have seen a null, after that, if you see a node, that means that is the problem. So what I'm saying, like say here there was a null. So as soon, so we are doing a breadth-first search. So we are going 1 will come, 2 will come, 3 will come, 3 will put null line 7, 4 will come, and 4 will also put 2 nulls, 5 will also put null, and this when this null will come here, we will set this end as true. After that, if 7 is coming, that means that is the problem.
Yeah.
Does that?
Yeah, got it.
Yeah.
Yep.
So in this case, null will come, but before that we have already processed everything. So we'll return true here. So at the end, if nulls are coming, it's okay. But after we have seen a null, if some node is coming, that is a problem. Does that clarify?
Yeah, that clarifies. Thank you.
And so Rajendra, your approach was also like this, or I think you were having a different approach.
I think my approach is a little different.
Yeah. That's what I understood. You are not putting nulls in the queue, right?
Yeah. I'm not putting nulls. I'm just, once I see a null, I set the flag up, and every time before putting the,
before putting you're doing, okay, got it.
already check it. If the flag is set, I should not have a child here. There should
Okay,
be
so
no left, no right. Yeah.
okay, my approach is you put null, and if you put null, after that, if you see a node, then that is a problem. Like line this one. So if you already seen a null, after that, if you are getting in the else block, then if all nulls are coming, we'll always hit this guy 17, 17, 17, like this 17 line. But if you're coming here, that means we have seen some not null node. And before that, if we have seen a null, that is a problem.
Yeah, mine was basically a little preemptive, so to say.
Yes. So you're not putting null, that is also good.
Yeah.
So instead of whenever he hits a null,
Hmm.
he's setting a flag.
Yeah.
And whenever he looks for that flag, and then he finds a node, then he says it's false.
Yes. I mean child, not node. There might be children. For example, suppose in the first example, there is a child of 4, suppose. Okay. So by the time I marked my flag at 3, when I saw that 3 doesn't have a right, I came to 4 and 4 have a child, then I know that is a problem because my flag is set. It should not have any children.
I think I have a similar implementation maybe then.
Okay, then
Do you want me to share? So actually we are very clear what he's talking. Is this something you're saying, Rajendra?
Like that only. Give me a second.
So I'm saying this check flag, whenever you come to any node, if you don't see the left, okay, you set the flag, okay, or if you don't see a right, you set this flag.
Yeah, correct.
And then when you come to this node, you see this flag and then you return false, right?
Correct. That is exactly what I was saying.
But both of the even his implementation is almost similar, only because I see a lot of code written over here, therefore.
Yeah, I mean, then it is just an art. Basically, you can preemptively check the flag first, and then you can go like that.
Okay, you just want to check it outside and then see it. Okay.
And somebody shared the first solution using like math square root. Can you put like in the code a chat if possible? Thank you.
Asim, you wanted the code from the chat, right?
Yeah, I think the first question, that prime one.
Oh, okay. Shashank is talking, but he's on mute. Shashank, can you unmute and talk?
Yeah, sure.
You were talking something, right? I think Asim
Is
had
it
some
audible
different
now?
question. Yeah, it is audible now. But Asim was
Okay.
talking something, yeah.
No, I was asking like somebody was sharing the first code using math.squareroot. I was wondering if we can put that in the chat.
Sandeep,
Oh yeah, I'll share it on the chat. Yeah.
Okay, thank you.
Yeah.
I think Shashank, you can go ahead. Thank you.
Yeah, sure. So yeah, it's like same like if you find that you hit a null and check like every node in the queue, if it is I mean if any of them is null, just return, it will return false from here and then just traverse to left and right. That's it. All means if none of them should be, if anyone you got fake one like false, it will return false for the entire.
Okay. So once you saw the node, you are not doing anything else. You are linearly probing it, the remaining of the queue.
Yeah.
Expecting none of them should be non-null.
Null. None of them should be null. I mean, if you hit null, you will be caught here, right?
None of them should be non-null, right?
I mean, node should be there. Yeah, sorry, like non-null. If you hit one null, then you'll come here and that will return false from this place. It will check in the queue that for even for one node, if you get a null, not of null. Oh, sorry, if you get a node and not of node is what, false. So it will return false for this. When you hit a node is null. Otherwise, it will never enter this condition.
Okay, so you're saying if you have any null and the queue is not empty, right?
Yeah.
Because you are not putting null in the queue.
I mean, literally, I'm not putting null. It's a way of check. Yeah.
But you are putting, right? You don't check that condition on 2021.
Yeah, he's checking actually. He's not checking. He's putting null.
Shashank, could you explain that line number 18 and 19 again, please?
Yeah, sure. It's like, let's say you inserted first root, one you inserted, right? Now you'll pop out of it, pop left, one will be popped out, and you will check if not, I mean, if that, whatever you have popped out of the queue, if that is not null, then again you'll go to left and right. But if you hit that, if it is a null, then it will enter here and it will check for all the nodes in the queue, like whether that's null or not. If it is null, not of null will be what? True. And if one of them is true, it will return from here that sorry. See, you inserted one to the queue, right?
Yeah.
Now you'll pop that node. Now you'll check the thing that you have popped out of the queue, whether it is null or node. If it is node, then it will not hit here and it will just continue for the left and the right. But moment it hits that it is a null, then it will go here and check. It will check for every node in the queue. And for every node in the queue.
So is it like when you hit the null,
Not of,
are you checking if there are nodes in the queue?
yeah, it's like that only.
Yeah,
Node for
because
every node in the queue.
if the queue is not empty, then only the this condition makes sense, right?
Yeah.
Yeah, I think that
Yes,
might be the same implementation. Return all, and then you are having that code.
Yeah.
I think what the line number 19 is doing is making sure if, I mean, line number 18 basically says, hey, I just saw a null. Line number 19 is saying, okay, if that is the case, everything, the all in the queue should be null now.
Yeah. Because I think it's just the not null is for the last level, I think, where 4, 5, and 7 you're inserting nulls.
Why there is while true here? Should not it be q dot empty, not q dot not empty?
Q dot?
Line number 16, while true. So
yeah,
I'm just wondering.
It will be an infinite loop, right? So you could have
will
done
continue till you hit the entire.
Yeah, I was wondering how the loop is ending. But the thing is, line number 17 basically pops nulls and everything. So basically, at the finally the queue will be empty. I mean, 18 will be hit anyhow. That's why it will return from there. Otherwise, 16 was not intuitive because it is an infinite loop.
So it has to return either
While
true or
while
false.
one.
Okay.
Yeah.
Cool.
This all is like if entire thing inside it is true, then it will return true. If an entire thing inside it is false, it will return false.
Yeah.
Or any confusion here, like?
No. That's good.
Yeah. Yeah, then we can switch to next. Next is like bitwise OR of subarrays. They have given A of non-negative integers. So for every contiguous subarray, this A of I plus 1 up to A of j, as long as I is less than j, we take the bitwise OR of all the elements in B, obtaining the result is, and return the number of possible results. And results that occur more than once are only encountered once in the final answer. So here it's 0 only, so only 1. But if we come here, the all possible sets they have generated, like all possible subarrays 1, 1, 2, 1, 1, 1, 2, 1, 1, 1, and 2, and they have calculated the what is it, binary of it, and if it is unique, I mean they have done the OR of it, and if it is unique, then they have written. So there are only 3 unique values, like 1, 1, 2, and 3 you'll have as unique. 1, 2, and alone, 1 you'll have unique, 2 you will have unique, and 1, 2 is also unique, because 1, 2 will be 3. But the moment you hit 1, 1, 2, it will always be a repeated something. Because 1 and 1 is 1, or 1 is 1, and 1 is again, this will be 3 only. 1, 2, and 1, 1, 2 will be 3. So only 3 values are here. Yeah. So any queries here?
Yeah, this problem looks not so straightforward.
Yeah.
Yeah.
It's like, yeah, go ahead.
No, I'm just saying it's not so straightforward. Yeah, but yeah, the possible subarray, whatever they are saying, it's okay.
The brute force is like finding all the combinations and doing a or.
Generating bitwise.
N square you can do it, right?
No, brute force will be 2 raised to the power n. No, because generating all the subarrays.
Subarrays, subsequence, or
Yeah, it's not subsequence. Subsequence is exponential.
Oh,
So if it is subarray, it should be n cube, right? Why should it be 2 raised to n?
I mean, you can start at I and you don't have to, I mean, you can just check whether.
Yeah, it's like 2 for loops, right? The first for
Yeah,
loop starts from I, and yeah, and the second for loop starts from where the first for loop started. Right?
yeah, kind of.
Yeah, but yeah, doing an OR maybe like because we are doing an OR operation also on each combination, so maybe n cube, worst case, right?
and
I
then again
mean,
checking the unique.
if you can add it to a set or something like that and do, I mean.
Yeah, so then, yeah, so I was thinking like when you add a set, you are actually trying to remove the duplicates, right?
Yeah.
So still
Yeah,
that
yeah.
tends to be like a optimized brute force option, right?
Yeah, kind of. Yeah.
Yeah. And that
People are
fits
using
well.
BP
Yeah, yeah.
also, you know.
And I think that works, the one what you said.
Whether there's an less than n square, we need to
Yeah.
find.
So even Sandeep said n cube, and then what you said, the modification of it, they both are almost good. They both are, I
Yeah,
think,
but
accepted.
bitwise, if you do some log factor can come, that can make it a bit more.
Really? Okay. I didn't
Yeah.
think about it. Yeah.
No, what I saw there in the discussion section.
Okay. So anyone, Sandeep or Uday, do you have something to share before
No,
starting?
I did not solve this.
Okay.
Yeah, so what this is what is like I created first 2 sets, okay? Yeah, go ahead. Yeah, 2 sets, and for every element, let's say whichever here, let's say because all 3 are unique. So what I'm doing, I'm taking each element. I think I'll have to write. It's like, so this is like my 1, 1 and sorry, 1, 2, and 4. It is right. So I have one set, initial set, and a result I have. So what I'm doing here is like initially, if you look, my set is empty, right? So
Okay.
first time I'll just what you say, add one to my set. Now
Mm-hmm.
next time what happen? I will go here. Now
Mm-hmm.
I'll do, and I'll add this also to my result.
Mm-hmm.
This is my current set every time here. Next time what I'll do one and with this. So when you do and with this one, sorry, or with this if you do, so it
Mm-hmm.
will be like what? One or two will be three, right? Yeah, it will be three. So three, I'm adding to my current set as well as I'm pushing that number which I'm using here. So my current set will have now 2 comma 3.
Okay. Uh-huh.
Next time I'm hitting 4. So I'll do or 4 or 2. 4 or 2 will be like 6, I think. 8, 4, yeah, it will be 6. And again 4 or 3 if you do, it will be 7, right?
Okay.
4, 8, 4, 2, 1. So 4 is this, and your 3 is what? This is 3. Yeah, it will be 7. This, and I'm pushing this number also. And to my result, whenever I do operations, I'll push 2 and 3 over here. And again, this I got in my current set, I'll push it to my result. So 1, 2, 3, 6, 7, and 4. I'll do XOR with this and then push inside. Like before pushing it inside the result array, I'll do ones or two. Ones or two will be what? 3. Now ones or 3 will be 3. So 3 I will not append. Now I'll do with 6 again. So it will take unique elements only in your result.
Are you doing XOR or OR?
Or I'm
Okay.
saying XOR by mistake here, or operation.
Okay.
So like initial result was having 1, right?
Mm-hmm.
Now in the current set I was having 2 and 3. Now while pushing it to the result, I'll do or with 1. 1 or 2 I'll do, then it will give 3, right?
Mm-hmm.
And again 1 or 3 you'll do, it will give 3. Since 3 is already there in the set, so it will not take. So by this way it is avoiding the duplicates. Next time
Okay.
whatever elements you do or with that. If you find that that is unique, then push it inside the array,
Mm-hmm.
or set, or if you find that it's repeated, then it won't. At last just take the length of this set.
Mm-hmm. So in all, you always have to check for each and every
Element
ORing that element, right? So you have to go through each and every element every time
of array. Yeah,
of that
I
array.
mean one time only I'm going through this array, but at any time in current you can have k elements. So n log k it could be at max.
Yeah. So yeah, you have to pick up only single element, but the set it keeps on increasing, no? Every by each and every element, if they are all unique
Element,
elements.
yeah.
Yeah. Right.
Hmm. Hmm.
So then it becomes a bigger number. Yeah.
Yeah, gradually array will become. It could be similar to n square or n log, something between them.
Yeah. Maybe.
Hmm.
So this
Yeah.
is your implementation.
No, I've checked in the discussion section and then.
Okay.
So I mean, it's very like understanding it was like not that trivial. Like the way they have uh, given it.
It is easy to get all these means understand how it is implemented,
Yeah, yeah, yeah.
but getting an optimized version is slightly difficult, right?
Difficult, exactly. Yeah.
Mhm. Because in the C++ section, they are actually using unordered set, and they are using the
Uh,
3 unordered sets. And in some
mhm.
cases, it hits a TLE, but with slight modifications, you can at least get accepted. Um,
Solution lead code. Yeah.
yeah, but the best way would be actually to use something like a vector and then at the end put it in a set, so for each and every level the way you are doing, you put it in a vector, so you don't care about the
Mhm.
what you say, the duplicates first. So at the end you put it in a set, then that slightly is a more optimized version, because if you try to keep on looking for duplicates at each and every level when you do this, putting it in a set, so then I think it
Yeah.
consumes more of operations. There might be movements a lot in that unordered set, the way it is implemented. But if you do it at the end, then actually it works better. But still not so great solution though.
And yeah, but still,
How it is on
some
off and I would ask that how it is off and log K, that because he is iterating for I in A also and then also here also. Then for set in insertion it takes log K. I know that, but how it is n log K? Should should not be n log
and
K.
I'm
No?
saying array of length of array is n, right? I mean, this let's say n elements are there in your array, okay?
Okay.
And at any time in your current set, every time element will keep on increasing, right? If I mean,
Yes.
if it is unique, then it will keep on increasing. So I was thinking that like k elements could go at max. K elements you can have at any time. It should be nk, not n log k.
Not n log K.
Log I was yeah. Log operation is for this, like doing the or operation, this or inside the or operation. It should be nk, not n log k. Yeah, sorry. Or what do you think? Like,
It should be. It should not. It should not be at n log K. It should be nk only.
nk, yeah, n log k one mistake, I think. Log operation is for doing just that or operation every time.
And in set insertion also it will not take any time because set insertion also takes some time because it is a red black tree.
Set operation, because of this only I'm doing. No, this or operation is only adding elements to the set, this single line, right? So that will only take log operation performing, I mean, converting to bits and checking if it is unique, then it will take it inside the set, else it will not. I mean,
I don't
like,
understand line 5. Can you?
pardon?
I don't understand line 5. Can you explain that again?
Yeah, sure. See what is like.
Maybe like use 112 as the example.
1 to 4 is our set, right? So initially our set is empty, current set, okay? So first time it's empty, just I inserted the first element inside my set. Now I'll go for the second one. And in res is also a set only, result. In that also I'll append 1 because nothing is there in your res initially. Now next when you hit 2, I'll just do OR with these two elements. So OR of 1 and 2 is what? 3. So I'll just put 3 and I'll append whichever element I was going over. So now your current element will current set will contain 3 and 2. Now when I put this result into my res, I'll again do the OR with this 1 or 3. 1 or 3 is what? 3. And 2 or 1 if you do, that is also 3. So it won't take this 3. So 1 and 3 you will have in your set. I mean result set till now. Now next time when you hit 4, you just do 4, 4 with 3. So 4 with 3 it comes out to be 6. Sorry, 7. And 4 with 2 if you do, it comes out to be 6. And again you append that element on which you were hovering. So 4 will also come here. And now whatever elements you have, take each element, do the ORing with this, again do OR with this. If you find that the result is unique, then you just append it, else you don't append that.
Yeah, I think this is okay. Can you go to the code?
Yeah, sure. So for every element in the J, this is the I is the current element index. And for every, whatever you have current element in your set, you do OR with your current element. So this will take the OR of that. And this is for appending the current index element. So if you have 2 and 3 in this set, then I mean, one was earlier. Now, when you did 2 with 1, you got 3 inside your set. And this is the element 2 I was ORing with this. So I'll append 2 to my current set here. And the same.
Just to clarify, let's say the very first time your current is empty, so then you will do I or with the empty and then
OR again with the first element. Is that right?
Yeah, pardon?
Maybe a dry run will be very helpful
Yes.
if you do dry run.
See, initially
Dry
I
run.
have first using the from like this only, no, or print statement by using.
Yes, yes.
Okay, so this, let's say initially your current set is empty, right? So you'll encounter the first element. So this won't be executed. This will be, or operation will be executed. So the empty set, the element at current index will be added. So one will be added. Now next time you will go to 2. Now what, for every element in your current, so your current is having 1, and this is the current index, like here you are. So 2 with 1 it will do. So 2 with 1, if it will do, it will be 3, and it will be 3. So your current will have 3, and this is the element that I'm inserting, at which I was, that is 2 I'm doing here, and this is what.
Wait, is 3, why is it 3 comma 2? Because isn't it 3 or with
Isn't
the 2? Isn't 3 bar 2?
No, it's
Why
not
is
3 power.
Huh?
I see 1 is what, 0 1,
Yeah,
right? The binary represented.
yeah,
I'm doing XOR with 2. 2 is what, 1 0.
yeah,
Now what is the XOR of or of these two? It will be 3,
3.
right?
Yeah, but where's the
So
comma come from?
where is the,
Where's the comma come from?
no, this is just for representing. I'm putting comma.
Oh, you're saying, okay, 3 or was
This is a set actually. When you enter one element, comma, it will take automatically, like, right? We don't need to put it.
Okay, yeah. So when I use in C++, if I use more sets, then I get I just cross. I'm on the border. It gets accepted though, but it's a very big number. But then
Okay.
because the set is used only to actually look for and remove the duplicates, right?
Duplicate.
Yeah.
Hmm.
So I found one implementation wherein actually they actually take into account all the duplicates. They don't care of it. Keep on doing it till the end.
Hmm.
And at the
Yeah.
end, you put in a set, so all the duplicates are removed. So that is more efficient. It's almost half the time. So
You
because
can
you are
share.
also using two sets, right?
Yeah.
So I
Exactly.
thought maybe like only one set, you don't use the set till the end.
Yeah.
Because someone was saying about set operations, right? It takes more time.
Yeah.
But in C++, if I use unordered set, it is O of n, but still there is some time constraint there. I think the implementation depends on the way we are using it. So you don't bother about the duplicates till you go to the end. Keep on doing it. Keep on adding it in a dynamic array or whatever the way you are doing it. And at the very end, you put in a set to remove the duplicates. So it might be a huge one. Just put in the set, then it removes the duplicates, and it's more efficient. That is at least I found in C++ implementation. I don't know about what's going to happen in Python.
Yeah.
Because I started with unordered sets a lot first initially, then it was giving always a TLE until I used one of their hack of actually that platform dependency of syncing to the studio and all that stuff. So I was getting accepted, but then I didn't like it, so I went looking for something else, and then I found like this people are saying if you put everything in a array the normal way, keep on doing it, and at the end you do remove the duplicates. Then it works, because every time in the intermediate step, every for loop you keep on removing the duplicates.
Yeah.
When you are putting in the rest right here on line 6, you are actually removing the duplicates also, correct?
Exactly.
So you are thinking like if I remove the duplicates, always good for me in the for loop. You are to take care of less elements, correct? So that is the reason you are removing. But
Yeah.
that
Exactly.
actually has a performance hit. That is what people say.
Yeah, it is having a memory limit.
Yeah. Rest, I think all implementations are exactly what you are showing, and there is no other way anyone thought of it.
DP I saw some like they
Yeah,
are
maybe something like that. I was thinking like you have that cumulative sum and prefix sum and all those things, right? Could do
exactly.
something that way.
Mm.
But yeah, so was there a DP solution also?
Me, I am no, I'm not having.
Okay, you saw that. Okay.
No. That set is, I mean, helping. That's it. That is the advantage we are getting over here.
No, set helps, but then there is other side of the set also.
Repercussion of it, yeah.
Yeah. But the implementation is straightforward. It's not very tricky. Just take each and every step, or it
So,
always.
yeah. Just curious, I mean, instead of that unordered set or something like that, if you use bit set or something like that, uh, still it would be like that?
No, I didn't try that. That would be a good thing to try.
Bit set.
Use a bit set, but then okay.
What is
Bit
bit
set is
set? Like,
basically you are setting for each and every bit, right? In bit.
Yeah, I mean, hash set, if you will have, you can, the chains can increase. I mean, that way the time will increase. But if you're, or I mean, bit set is something like a vector of integers itself, but it uses particular bit to check whether that is existing or not.
so corresponding to that number, you set bit as 1 if it is existing.
Yeah, it's like that itself. Yeah, bit set.
Okay.
So whether I mean, if it is existing or not, it will just be a bit set. But memory, I'm not sure of. I have to check.
That is only bit masking, right? Bit set is only bit masking. In that
Yeah,
also, yeah.
yeah, bit mask.
Yeah, I don't know, but if the number is something bigger, then how bit set will help? That is what I was thinking. If it is bigger than 32 bit.
This, yeah. So
No,
what's the
no, no,
problem? 64 is there now.
I think bit set actually internally uses some vector or something like that internally to have additional values. It can dynamically increase its size.
Okay.
But I mean, yes, you said the memory can be a problem.
Yeah, I think this is a good solution. I can quickly show you what I
Yeah,
did.
sure.
Yeah. Yeah, I tried other ways also. I started with this way. Okay, it was unordered set earlier, but then I thought of using ordered set. So still it gave me TLE. Same thing what you are doing, Shashank here,
Yeah.
I'm doing it here more line of code, so and then you add, but I'm adding it to the answer here itself. That was one thing, it was hitting a TLE, so I went this route wherein small things, small optimization, but this was also not so good. Almost the same
What is the
implementation
sync
using.
with audio?
Sorry.
What is that line number 62?
Oh, this one is some optimization for this lead code on the C++ platform. If you sync with these streams, the input and output streams, you untie them and all those stuff, because it actually, has some problems synchronizing with the STDIOs and IO bases, those two streams.
Oh,
You just decouple them, then it works fine. That is an optimization, but it's nothing to do with the code.
I
So,
thought iOS some platform something. It's input
uh,
output, right?
Yeah, these are the input
I was
normal.
yeah. Okay.
See in and see out the way you actually put it on a console, and then you take it
Yeah.
from the console. Yeah, the standard input. So this actually the code where actually you have three sets. One is the answer set, which is for the result RES what you are using, and these previous and the current actually are the intermediate ones. Nothing big deal about it. You just take something, whatever is the value from the A, and then you keep on inserting it. You store it in the previous for the next version, right? And then you put the answer. So the previous actually it comes here, right? So for the next one you are taking from the previous, something like that. So yeah, this is fine, but you are using three sets, and that was a problem. So when I actually went ahead and found here, people talking about using a vector, and just pushing everything in a vector every time. Don't worry about all the duplicates till the end, completely do this. And every time you're putting in a vector, you need to have the indexes, start and end indexes. So this is the way you get for each and every iteration, you store those start and end indexes. So you can use it for the next iteration from here, right? So the vector remains same, that is array remains same, but you are just pushing it like a level order traversal, right, in the queue, sort of. And then you come down, and here you use set, and then you put everything in the set, then it removes the duplicate, and then you return. So once you are using only set once, then the performance decreases almost by, it's a good performance. It's like half of the time actually it takes
Yes.
to do this. Yeah.
Uh,
So that was one I found much useful. So this is another way using XOR. Sorry, not XOR, but unordered. Yeah.
Yeah, I also thought XOR, that XORs you are writing. That is X or S, right? X or S, right? Line number 19.
No, actually, I renamed this set here as XORs. Yeah.
Okay, okay,
Yeah, this the variable name is nothing to do with that.
okay. Mhm.
So, but this implementation is the best implementation. You put it in the vector, and then you use set only at the end, so to remove the duplicates. Then actually it gives a very good performance.
Oh,
So that is what I was trying to say. If you do it this way, in your case also, instead of using a two set, if you use only single set for the answer at the end, then it might be
mhm.
much better.
But how will we keep track of current elements? How much?
So here it is doing, right. It's using start and end. So these are the two indexes. So whenever you come inside this array, you first
Hmm.
you set the start and end to 0, correct? So now
Okay.
you actually finish the whole loop here. So you just take the start, the previous value of end, but
Hmm.
the end will be the current size of the vector. So where you have entered.
Yeah.
So you again go here, so you know now what your end was, start is now, and what is your end. And then again it increments, then so keep on changing that. So you are actually moving, right?
Yeah, exactly. Mhm.
And at the end you actually put that in a set and then you return. So this is a good performance, at least on the C++ side, C++ side. So I'm not sure what it is on Python.
I have to check in
Yeah,
Python. I mean,
yeah. Maybe if you instead of two sets you use one set, it might slightly give you a
optimize
performance
better.
improvement. Yeah. Yeah, but the some implementation, the problem statement and the implementation is not of a big deal, right? The way it is talking about exactly the way we have to do what they are describing.
Do.
Yeah, nothing fancy.
Mhm.
Only using all these things efficiently that actually shows your implementation skills.
Yeah, it's a line.
Okay,
So it will be also n square only, right?
this one.
I mean, the one like line 40 n, that will be n, and then inside you are running 43 start to end.
I don't know. It might be more also.
Uh,
Yeah, because
yeah,
every time you are increasing the number of
size,
whatever
yeah,
the things you
start
are,
and end, yeah.
yeah. So, but
I
that's
think
what
it
it is.
was
So can't help,
yeah.
because
Yeah,
inner
we'll
for
try
loop actually keeps on increasing, no?
increasing. Yeah, that is the
Yeah,
problem.
yeah. So, but if you look at the
But again, it is avoiding duplicates also. Inner, no,
no,
in
it is
mine.
not avoiding
Yeah, no,
duplicate.
no, no. In mine case, it was doing the
Yeah,
current set was avoiding. Yeah.
yeah. Here only it looks at the end to see if there are any duplicates. To
Duplicates.
some extent, it tries to avoid it. It looks at the end. If it is not equal to the current one, then only you push it. So to some extent it does, but not all.
Yeah.
But in your case also, if you look, they say like n log w or something, right? In the solutions, what they have mentioned,
Yeah.
time complexity, n is the length of the array, and w is the maximum size of elements in A, right? So that is what it says. Frankly, I didn't get that. Why are they saying that?
That bits. I mean, I didn't get like.
So if you look at the time complexity in the solution, so they say it is n log w, right?
Yeah, and log
Yeah.
W. Yeah.
So I didn't understand why they are saying like that.
I think this start and end that might be taking log W and upper one end. But again, how this is because
No,
they are
not in
using
my
all
case.
of this.
Actually, it is in your case, because the way
Yeah.
you are doing it, you are using set,
Yeah.
dash set, right?
Yeah. Exactly.
Mm.
Yeah. And what they have given as a solution?
The time complexity is n log w.
Uh, So maximum size of a current set will be W. That is what's saying.
Yeah.
And that log factor I know is becoming because of this, or I mean, whenever you use bit operation, that log factor will come. So here they are considering like W elements at max can W unique elements can enter your current set. So and for every each of them I have to find or with the next number. So might be this is log W and n log W. But somebody was saying n into k. I think W is the maximum size of elements in A.
Yeah, I also think it might be slightly more, but yeah. But if they are saying here, it might be,
Definitely, yeah, something
yeah,
is
they have verified it properly before writing. Yeah, no problem. Yeah, that was a great discussion. Thank you. Thank you,
no.
Shashank. Yeah, thank you.
Thanks, Santosh.
Thank you. Bye.
Thank you, guys.
Thank you, guys. Yeah.
Thank you.